In this set of notes, which is the first set of notes in the Unit or Topic 3 material, we're going to talk about limits at infinity. So we're going to, of course, define what that is. We're going to talk about some rules that were going to help us in computing these types of limits. We're going to go back to our rational functions and talk about how to simplify them, kind of like what we did in the Topic 2 material, spend a little time with our rational functions because sometimes they can give us trouble. And then at the end, we're going to talk a little bit about this idea of indeterminate forms, which we will see later in the course, but they kind of start showing up here, so it's worth mentioning at this stage as well. All right, so to get us started, it helps to think about what we've been talking about up until this point. So we've been dealing, of course, a lot with limits, and up until now, every time we've evaluated a limit of this form, the limit as x goes to a of some function, a has been finite. So it's been some number like 4 or 2 or 1. Even in cases where we've been dealing with, say, one-sided limits, it's been evaluating the limit as x goes to 2 from the right, or 5 from the left, or something like that. They've all been finite. There are times, though, where we might want to use limits to describe the long-term behavior of a function. And if that sounds somewhat familiar, if you go back to that should be a 2.1 notes, we talked very briefly about the long-term or end behavior of a function. And let me actually just bring that up here. Go all the way back to page 2/3. So we had this function f of x equals 1 over x plus 1. We talked about this local behavior, which was describing how the function behaves as x approaches a specific value. And we talked about this long-term behavior at the top of page 3 as the behavior of the function as x, the input, increases or decreases without bound, or in other words, as it tends toward positive or negative infinity. And that's really what our focus is going to be in this first set of notes in Unit 3, is what's going on with a function as we let x go to either positive or negative infinity, that end or long-term behavior. So we want to describe the behavior of our function as x increases either positive or negative without bound. So that's the specific focus of this set of notes. Now, just a quick note here, because sometimes these can sound similar. This is limits at infinity. In the previous, again, this should be a 2, sorry. In the 2.1 notes, we talked about infinite limits. Infinite limits, what we already have done, are cases where the limit value itself goes to infinity, positive or negative. Infinite limits at infinity, what we're going to be talking about now, are what's going on when we're letting the input or taking the limit as x goes to infinity. So infinite limits are cases where the limit calculation ends up being positive or negative infinity. Limits at infinity are cases where our input is going to positive or negative infinity. Just to kind of clarify that, because they sound a little similar, but they are quite different things. So let's look at limits at infinity. So as always, it's a good idea to just give a brief definition here. We've already sort of talked about this, but just to give it a formal definition. Suppose we have a function f, we have this a acting as a real number, and we have f defined over an interval, say, from that real number a to infinity. We say that L is the limit at infinity of the function if we can make f of x, like we've talked about, arbitrarily close to L by making x sufficiently large, and in this case positive. So again, like we were just talking about, putting all of that into an expression, which is usually how we're going to see it, a mathematical expression, that's us taking the limit of f of x as x goes to infinity. And this thing can be finite, it can be infinite, capital L, it depends on the function. So as x goes to infinity, as it increases without bound, we could have a finite limit value, or we could even have an infinite limit value there. Depends on the function. Same thing in the other direction. If we're making x sufficiently large in the negative direction, then we can have this calculation, limit of f of x as x goes to negative infinity increases in the negative direction without bound. And that can also, again, give us either a finite limit value L or positive or negative infinity. It depends on the function. So a lot of the rules and techniques and things that we've talked about can apply to limits at infinity. But there are a couple things worth noting. Some of these are a little bit reiterated from before, but some of them are new, that are useful when we're considering these specific types of limits, letting x go to positive or negative infinity. So let's go over those briefly here. And again, some of these are repetitive from the previous sets of notes. I just want to reiterate them to show that they do still hold in these sorts of cases. So first one here, again, if we have a constant function, if it's 5, if it's 29, if it's 807, even if we're taking the limit as x goes to infinity, well, there is no x in the function, so the limit doesn't do anything. The limit at infinity of a constant is just equal to whatever the constant is. These are rules that we saw before for finite values of x. As x goes to infinity, we can still break up a sum or a difference of limits. The limit at infinity of the sum or difference of two functions is equal to the sum or difference of the limits. We saw this back in the first set of notes. Same thing with our product. If we're taking the limit as x goes to infinity of a function times a function, the limit of that product of two functions is equal to the product of the limits. So breaking it up into the limit of each piece of the function, each piece of the product. Another one that we've seen before. Two other ones we've seen before when we've got a division or a ratio of functions, the limit of the division of two functions is equal to the division of the limits, provided that this denominator limit is not equal to 0. And our fifth one here, if we're taking the limit as x goes to infinity of a function raised to the power r, then we can take the limit of that function and raise the resulting limit value to the power r. And of course, these give us the same sort of results if we're taking the limit as x goes to negative infinity. Now, two additional rules here that can be extra helpful when we're talking about limits at infinity are these rules 6 and 7. So let's let r be a rational number and let r be greater than 0. Then if we're taking the limit of this function 1 over x to the r, as x goes to infinity, that limit's going to be 0. So like if this is the function 1 over x to the 4th or 1 over x to the 7th. Basically what's going on here is this denominator expression as x goes to infinity is going to grow. It's going to get bigger and bigger and bigger. It's going to overwhelm that fraction. That whole fraction is going to go to 0. This is another one of those things I think we talked about like in the first set of notes, that if you're like, I'm not really sure what is going on, it can help to look at a calculator and just say, oh, well, what happens if I take, say, 1 divided by 2,000 or 20,000? Pretty small number. What if I take 1 divided by something even bigger? Oh, that fraction is going to get smaller and smaller and smaller. And if I take that limit as x goes to infinity, that limit's going to go to 0. And one that maybe is a little bit more obvious, if r is greater than 0, if we're taking the limit as x goes to of x to the r as x goes to infinity, then this thing is just going to blow up on its own. That limit's going to be infinity. So like x to the 4th or x to the 7th, as x gets bigger and bigger and bigger, that whole expression's going to grow without bound. So just a couple additional ones that can be helpful. Now we'll do, of course, some actual examples here in a second, but let's briefly talk a little bit about our rational functions. So like we talked about when we were first introducing limits, we saw that sometimes rational functions can give us trouble just because of the way they're set up, that ratio of a polynomial over a polynomial. We have that same sort of thing going on here with limits at infinity, but ratio or rational functions also allow us in some cases to use a nice little trick, which can really shorten our computation time, as we'll see in a couple examples. So let's use this to demonstrate what I'm talking about. So here we're taking the limit as x goes to infinity of this rational function, a polynomial divided by another polynomial. Now notice that both our denominator and our numerator terms involve x squared and just plain old x and just some plain old constants. Now as x tends towards infinity, what we're doing with our limit here, the x squared terms are going to grow faster than just the plain old x terms, and of course faster than the constants because the constants aren't going to grow at all. And the x squared terms are going to dominate both the numerator and the denominator. So much so that they're basically going to overwhelm our calculation. The other components, the x pieces, the constants, are going to basically become irrelevant to our limit calculation. And this is true in general, and this gives us a nice little shortcut. For any expression, for any rational function, the coefficients or the pieces with the largest exponents or the highest degrees are going to dominate as we take a limit at infinity, as x goes to positive or negative infinity. So a nice trick that we can use when we're calculating limits at infinity for rational expressions is to just isolate the terms with the highest degrees. Just look at those. And one way that you can do this is you can divide the numerator and the denominator terms by those highest degree terms, specifically the one in the denominator. And we'll see why this, you can kind of think of this intuitively when it's the case with the numerator, but for this trick, it helps to think about just looking at the denominator. What's the highest degree term in the denominator? That will get us to our result. Now let's use this to demonstrate that and do our actual limit, our first limit calculation where we're taking x to positive infinity. So let's calculate this limit. The limit as x goes to positive infinity of 2x squared minus x plus 1 over 3x squared plus 2x minus 4. So let's use our trick. What I'm going to do is I'm going to look at my highest degree term in the denominator. So what piece of the denominator has the largest exponent associated with it? And that's this here, right? 3x squared. So the highest degree term in the denominator is this 3x squared, or specifically the x squared part. That's the thing with the degree or the exponent. So this trick is going to let me do the following. When I'm calculating the limit as x goes to infinity of 2x squared minus x plus 1 over 3x squared plus 2x plus 4 is I'm going to now divide both my numerator and my denominator by this highest degree term, or specifically the x squared piece. So I'm going to take this numerator, divide it by x squared. I'm going to do the same for the denominator. And what that basically means is each of my pieces in these expressions, each component, each term is going to be divided by x squared. So I have 2x squared now divided by x squared, I'm looking at my numerator here, minus x divided by x squared plus 1 divided by x squared. So I'm just doing that division to all the pieces in my numerator. Denominator, same thing, 3x squared divided by x squared plus 2x divided by x squared plus 4 divided by x squared. Now, I start seeing some things cancel out. Firstly, in these first highest degree terms, the x squareds completely cancel themselves out. Here, this x is going to cancel with one of these squares. This x is going to cancel with one of these squares. And I'm going to have, I'll write this down here, the limit as x goes to infinity of, well, if those x squares cancel out, that's going to leave me with a 2. then this is going to be minus 1 over x, and this plus 1 over x squared, that doesn't change. And then on my denominator, those x squareds cancel out. I'm left with 3 plus 2 over x plus 4 over x squared. Now at this stage, we can try to take our limit, right? So I just should have done this at the start, but if I think about just trying to plug in infinity, or think about what happens as x goes to infinity here, like using the substitution rule, it might not be completely obvious how this would work out, what would be the final result. But once we start doing that at this stage, it starts to become a little bit clearer. The 2 and the 3, they don't have an x in them, so they're not going to do anything. 1 over x, well, x is going to infinity, so this fraction is going to go to 0. 1 over x squared, also going to go to 0, because the 1 is being overwhelmed by that larger and larger denominator. Fraction is going to go to 0. 2 over x, also going to go to 0. And 4 over x squared, also going to go to 0 as x gets larger and larger and larger. So basically what we're left with is just those leading terms, the 2 on the numerator and the 3 on the denominator. And that's going to be my limit, 2/3. So that's a nice trick that we can use with this type of expression, these rational functions. And we can actually even shorten it further. So this is like a little shortcut. Our trick is above. Here's an even faster way to implement it. Notice that our end result is just the ratio of those leading coefficients. In other words, it's a ratio of the coefficients of the polynomials with the largest same degree. So in this case, my two largest degree terms were 2x squared and 3x squared. I was basically able to ignore everything but those two leading coefficients, the 2 and the 3, because everything else became irrelevant. Everything else dropped out of the meaningfulness when we're talking about letting x go to infinity. So it's just going to be, in that specific type of case, the limit is going to be equal to the ratio of those leading coefficients. Now that's the case if they match. So they did in this case, right? X squared matches with x squared, numerator and denominator. If those leading coefficients are different, like this is 2 to the x cubed over 3 to the x squared, then that doesn't necessarily hold. We might have to do something else. But when there's the same highest degree term in the numerator and denominator, in this case x squared, we're able to just shorten everything to just those two coefficients for those terms, which is a really nice thing to do. It makes life a little bit faster when you're doing these sorts of calculations, if you can do that. So let's do a couple more examples here on page 5, and then we'll talk a little bit about some extra stuff involving infinity that can be useful in certain cases. So let's look at this one. The limit as x goes to infinity of 4x cubed plus 2x minus 1 over 6x cubed plus 10. All right, so first thing I'm going to do, again, if I just try to plug in x going to infinity here, it's substitution rule, doesn't really work that well. So I'm going to try to do this trick from above. I'm going to consider the case where I'm going to look for the highest degree term in my denominator. And in this case, the highest degree term, or the largest x exponent in my denominator, is this x cubed, right? So highest degree term, or if it's easier to think about it this way, the largest, I'll say x exponent in the denominator is, in this case, x cubed, right? It's got the largest exponent in the denominator. So let's do this using the trick, and then we'll see if we get the same thing using the shortcut. So this is the limit as x goes to infinity of, I'm just going to rewrite my expression here, 4 times x cubed plus 2x minus 1, all divided by 6x cubed plus 10. Now my trick tells me that I'm going to divide both my numerator and my denominator by this thing, right? The largest degree term in my denominator. So I'm going to divide my numerator by x cubed, and I'm going to divide my denominator by x cubed. So the limit as x goes to infinity is now going to be the limit of 4x cubed divided by x cubed. I'm distributing this division throughout, plus 2x divided by x cubed minus 1 divided by x cubed. There's my numerator. My denominator, same thing. 6x cubed divided by x cubed plus 10 divided by x cubed. Now let's see what cancels. So these x cubes are going to cancel. That x is going to cancel with one of these. These x cubes are going to cancel. So we're going to be left with the limit as x goes to infinity of 4 plus 2 over x squared. Move this over here a little bit more. Minus 1 over x cubed, all divided by 6 plus 10 to the x cubed. So what happens when I try to take this limit? Well, this is going to go to 0. Those x's are going to dominate that fraction, drag it to 0 as x gets bigger. This is going to go to 0, and this is going to go to 0. So what we're left with here is 4/6, or 2/3. You can reduce it if you want to. Web work will take this or the reduced fraction, as long as you're writing it clearly on a midterm, or your simplified version shows up as a multiple choice, that should be fine. 4/6, 2/3, either one's fine. But that's our limit. Now, just to show this, we can also do this much faster if we notice the shortcut way. So again, just writing down our original calculation, the limit as x goes to infinity of 4x cubed plus 2x minus 1 over 6x cubed plus 10. Now what's our shortcut? Well, our shortcut tells us that we can basically just ignore everything but the ratio of the leading coefficients. The leading coefficients, the top or highest x exponents, are this 4 times x cubed and this 6 times x cubed. So I can basically just ignore everything but those first terms, which is going to give me the limit as x goes to infinity of just 4x cubed over 6x cubed. Well, those x cubed terms are going to cancel each other out, and we're left with a limit of 4/6, or again, 2/3. Either one, I'll just write that on here too. Either one is fine. So if you can recognize when to use the shortcut, it is a lot faster than just the trick by itself, but they'll both get you to the same thing. So I'll just put this kind of in little brackets here. That's our shortcut. Let's look at this next one. So here we're taking the limit as x goes to infinity of 3x squared minus 2x divided by x cubed minus 50. And I'm going to do the same sort of thing. I'm going to try to employ my trick. My highest degree term in the denominator is x cubed. And so just like we did above, if I want to calculate this limit, the limit as x goes to infinity, I'm going to divide each component each coefficient or each piece by x cubed. So 3x squared divided by x cubed minus 2x divided by x cubed all over x cubed divided by x cubed minus 50 over x cubed. So this is the limit as x goes to infinity of these two x squares are going to cancel with two of those. These are going to cancel each other out. This x is going to cancel with one of these. And we're left with 3 over x minus 2 over x squared all over 1 minus 50 over x cubed. Now, what goes to 0? Well, this thing would go to 0. This piece would go to 0. This piece would go to 0. The only thing that's not going to 0 is that 1. So if I try to use my substitution rule here at this point, or I see what's going on here, I'm going to have this 0 over 1 minus 0, 0 over 1, which just means that this limit is equal to 0. Now I can't use my shortcut this thing up here because my numerator and denominator terms did not have the same degree. One was x cubed, one was x squared. So I'm not going to do the shortcut here, but let's just see if this makes intuitive sense based on what we were just talking about, this growth without bound. So notice that my denominator term has a higher degree than my highest numerator term. I have x cubed versus x squared, which means that even though that x squared piece is going to be growing quite a bit, the x cubed piece is growing faster, and it's going to overwhelm the numerator, essentially. It's going to grow faster and faster and faster, overwhelming the numerator, giving us that 0 over 1. So that overwhelmed numerator that can't fly, that can't do anything, it's going to go to 0, meaning the whole limit is going to go to 0. That denominator of 1 is enough in this case because the numerator itself is 0. Let's look at one more, then we'll talk a little bit more about some stuff involving infinity, because sometimes infinity and the concept of infinity can be a little tricky. So let's look at one where we're taking the limit of x goes to negative infinity of 4x to the fourth minus x cubed plus 1 over x cubed minus 2x minus 5. Now again, notice that our numerator and denominator highest degree terms aren't the same. We have an x to the fourth in our numerator, we have an x cubed in our denominator. But we can still use our shortcut. So I'm still going to look at that highest degree term. But again, remember it's specifically in the denominator. So specifically what's going on down here. So it's not the highest degree term in the whole expression, it's the highest degree term in the denominator, which in this case is, again, x cubed. So remember when we're using this trick, we used it here. I should write it because we used it here. And we used it in the first example. Remember, we're always dividing by the highest degree term in the denominator, even if it's not the highest degree term in the whole expression. So 4x to the fourth minus x cubed plus 1 divided by x cubed minus 2x minus 5. And we're dividing both the numerator and the denominator by x cubed. So that gives us the limit as x goes to negative infinity of 4x to the fourth divided by x cubed minus x cubed divided by x cubed plus 1 divided by x cubed, all divided, so that's all my numerator, all divided by x cubed minus 2x divided by x cubed minus 5. Let's simplify that a little bit. Let's get rid of those terms that are going to cancel. So all of these are going to cancel with 3 of those. These are going to cancel each other out. These are going to cancel each other out. One of these is going to cancel with one of these, leaving us with 4x minus 1 plus 1 over x cubed divided by 1 minus 2 over x. Oops, sorry, this should be 5. Sorry about that. 5 divided by x cubed. We want to do it on all of our terms. And that's 2 over x squared, because only one of those x's is canceling here. All right, so what's going on here? So even though this is going to negative infinity, that same pattern holds for our fractions, where we've got 1 over x cubed. Even though x is going negative, increasing without bound in the negative direction, that doesn't change the fact that this fraction goes to 0. Same with this one, it's going to go to 0. Same with this one, it's going to go to 0. And so what we're left with now is a nice simple function. The limit as x goes to negative infinity of 4 times x minus 1 over 1, or just 4x minus 1. Now this is where we do have to be careful with this limit value. So we're letting x go to negative infinity. And how is that going to change things here? Well, this is where we kind of cheat a little bit. I've mentioned before that infinity or negative infinity, they're not actually numbers, right? They're basically describing tendency or behavior. Something going to negative infinity is increasing without bound in the negative direction. Something going toward positive infinity is increasing without bound in the positive direction. So infinity is not a number, but sometimes it helps to kind of cheat and treat it as a number when you're simplifying things, just to make it maybe a little bit easier to visualize or conceptualize. So what's going on here is, if I think about the substitution rule, what I'm subbing in is a negative infinity here for x. Now again, negative infinity is not a number, but I can think about this term as being a negative term. It's increasing without bound in the negative direction. This minus 1, who cares? It's not really doing anything when we're talking about a value going to positive or negative infinity, so we don't really care about it. But what's going on here is we have something going to infinity in the negative direction, and we're just multiplying it by 4. That 4 is also kind of inconsequential. It's getting overwhelmed. It's going to just make the increase to the negative side faster. So when we think about this limit, it is just going to be negative infinity. And negative because we are increasing without bound in the negative direction. So this limit is negative infinity. The function's going to go and decrease without bound as we let x decrease without bound, or increase in the negative direction. So like I mentioned, sometimes infinity can be kind of a weird concept to work with, so it's worth noting just a couple operations that are worth keeping in mind when you're dealing with things that are increasing or decreasing without bound. So here are just a few general operations to keep in mind that might be useful in some cases where you're, again, ending up calculating limits involving positive or negative infinity. So if you take something increasing without bound and you add a constant to it, doesn't change what's going on, it's still increasing without bound. If you add two things increasing toward positive infinity, that thing's going to increase toward positive infinity. If you add two things that are increasing in the negative direction, so toward negative infinity, basically you can think about, let me rewrite this, you can think about this as negating the addition of two positive ones, which gives you the negation of positive infinity. If you multiply positive or negative infinity by 1, you get the same thing back, positive or negative infinity. However, if you multiply by -1 or any negative number, the sign flips. So positive infinity times -1 becomes negative infinity times -1 or negative anything becomes positive infinity. If you multiply two things increasing to positive infinity together, you get something increasing to positive infinity. If you have something like this, where you have something increasing times something else increasing times -1, basically is what this ends up being, you get something positive times -1, which gives you that negative infinity. So just some things worth keeping in mind, because sometimes you will run into one of these operations, so it's worth noting like what the result is. Now, if we take a look at this list, there are some things that are missing, and probably the most visible one is this, infinity minus infinity. And there's a reason for that. There's a reason that one's missing. It's actually one of several expressions that we typically call something that is an indeterminate form. Now, we're not going to run too much into this here. We will, of course, see some examples of this just so you know how to deal with it. We will have a much faster and easier way to deal with these types of forms later. Those of you who have a little bit of experience with calculus might know what I'm talking about when I mention the indeterminate form and this thing that we're going to be doing later with it. But we are going to introduce it here just because they are some things we can run into even at this stage, and so it's important to know how to deal with some of them at this point. So when we talk about an expression of indeterminate form, we're basically talking about some expression where direct substitution, even after manipulation of the function, basically just doesn't give us enough information to be able to directly determine the value of the limit. Essentially, it's a case where the expression, even when we do substitution, even after we've done some stuff to it, is still vague in terms of what the actual limit might be. So one of these is that infinity minus infinity. Other forms of this type are things like 0 over 0, infinity over infinity, 0 times infinity, 1 to the infinity, 0 to the 0, infinity to the 0. Basically, it's all those weird little math things you probably did as a kid just to play around with weird sounding numbers like 1 to the infinity or infinity to the 0, things like that. So we actually have already seen this, we just didn't call it this yet. We saw some of these 0 over 0 forms in the 2.2 notes. We will, of course, see them later. We'll learn a technique actually involving calculus to deal with them. But for now, if we run into these sort of expressions, basically our job is to try to get them into another form so that we no longer have an indeterminate form, so we can actually calculate the limit. And just like we were doing in the 2.1 notes when we encountered that 0 over 0 form, we have a couple techniques that we can use to deal with this. We can try factoring, we can try rationalizing, we can find that common denominator, or we could use some of these rules that we just talked about in terms of dealing with infinity, because of course right now we're dealing with this idea of limits at infinity, so we're going to be seeing infinity here a couple times. So let's take what we've learned here, what we've done already with limits at infinity and this idea of an indeterminate form, and just do a couple more examples here where maybe we need to manipulate the function a little bit in order to be able to actually calculate the limit. So let's look at this first example here on page 7. We want to find the limit as x goes to infinity of x to the 4th minus x squared. Now, as always, as we've talked about, it's a good idea to just try substitution just to start with, because again, as we've seen, if substitution works, it's fast, it's easy, you don't have to even manipulate your function. You can just go and plug in your limit value and evaluate the expression. So I always recommend trying substitution first just to see if it'll work, because sometimes it will. But in this case, if we think about doing substitution, we have, again, sometimes it's easy to think of, or it's useful to think of infinity as a number, even though it's not. Sometimes we kind of treat it as one just to plug it into an expression. So It's a little hypocritical because it's actually not a number, but we're going to treat it as one when we do our substitution here. Infinity to the fourth, that's just something increasing without bound raised to the fourth. It's going to increase without bound faster. And infinity squared is just something increasing without bound raised to the 2. So we've basically got this infinity minus infinity form. And as we just mentioned on the previous page, that is an indeterminate form. That's this one, which basically means we can't know what this limit is. Infinity minus infinity might look like it would be 0, but in terms of things increase, this is where it helps to think of infinity as a behavior rather than a number. This thing might be going to infinity faster or slower than this thing. So subtracting one from the other might not actually give us 0. So this is a case where we're in trouble. We can't just do anything with this directly. So let's see if we can do some sort of operation to this function that will get us to a form that we can figure out this limit. Now, this is a pretty simple looking function, and if I look at this and I think, well, what can I do to this? Maybe the first thing that comes to your mind is, well, there's a common x squared to these terms. So let's see if we can just factor out an x squared, see if that actually gets us somewhere. So let's do that. I'm going to take the limit as x goes to infinity. I'm going to factor out that common x squared, which is going to leave me with x squared minus 1. Now, again, at this stage, sometimes it helps to try substitution and see if that will get us somewhere. So this x squared, that's just something going to infinity. This x squared minus 1, we have something going to infinity minus 1. The minus 1 isn't going to change the fact that that thing is going to infinity, increasing without bound. So this term you can also think of as going to infinity. And notice what we have now. We've rewritten this expression, so we've got this infinity times infinity. Again, kind of treating it like a number, even though it's more of a behavior. But infinity times infinity, we just learned about that. That actually is something increasing without bound. Multiplying something increasing without bound with something else increasing without bound is yet another thing increasing without bound. So we've changed this from an indeterminate form to something that follows a rule or an expression that gives us an answer, something that we can actually calculate. And in this case, that answer, that limit, is positive infinity. So relatively easy manipulation for this expression to get us into something that we can actually evaluate in terms of the limit. Let's look at this next example on the same page. So now we're finding the limit as x goes to, be careful here, negative infinity of the square root of x squared plus 2, that whole thing plus x. Now this is a little bit more of a complicated expression. It's not too bad. But let's kind of figure this out here as we try substitution and see what that does for us. Now, just to make this a little bit easier to break down, if I think about this term under the square root, I have this x squared, which is, again, treating infinity kind of like a number here. Negative infinity times negative infinity, because my limit's going to negative infinity. That gives me infinity. Square root of something going to infinity plus 2 is still something going to infinity. And this little x here, just on its own, is going to negative infinity. And then I'm adding those two things together. So with substitution, I basically have something going to infinity plus something going to negative infinity, which is that indeterminate form we just saw, infinity minus infinity, which, like we just said, we can't really do anything with. So just like the previous example, I want to get it out of this form, this indeterminate form, into something where I can actually compute a limit. Now this one might look a little trickier because we can't really factor anything out here. We've got this square root term. Square roots can sometimes be a little tricky, but it might help to rewrite this just a little bit so that maybe we can figure out something that we can do with this that we've actually done with a previous function in another example. So let me rewrite this. The limit as x goes to negative infinity. Now my function is this square root of x squared plus 2 plus x. Now I'm going to do a little trick here that might make this a little bit easier to work with. And I'm just going to treat this thing as a fraction. Because actually, technically, it is a fraction. It's this thing divided by 1, right? That's a really obnoxious way to write that expression, but I'm writing it as a fraction. And part of the reason I'm doing that is because if we go back to the, let's see, the 2.2 notes here, and we talked about some examples. One of the techniques we talked about was the idea of rationalizing a function by multiplying a numerator and denominator by the conjugate. And I mentioned when we did this set of notes that this is very commonly useful when one of the terms involves a square root component. So just to refresh our memory here, we did this in example 2.2.7 on page 7 of the 2.2 notes. We had this rational function, this fraction, and we multiplied the numerator and denominator by the conjugate of the piece, in this case the numerator, that had the square root term in it. And we're actually going to do that exact same thing here. So even though our limit here was finite and now it's infinite, negative infinity, we can still use this technique. And part of the reason I wrote this as a fraction, that term over 1, is just to make it a little bit easier to see that this is technically a rational expression. We just usually just write it without that denominator because the denominator is just 1. So I'm going to take my numerator and I'm going to multiply it by the conjugate of the piece with the square root. And remember, the conjugate is going to be, in this case, we have this x squared plus 2. I'm going to keep that as a plus because it's under the square root, but I'm going to change this plus to a negative or a minus. That's the conjugate of that numerator. And I'm going to do the same thing to the denominator, square root of x squared plus 2 minus x. And now, just like we did way back in the 2.2 notes, I'm going to go ahead and FOIL my numerator to get rid of that square root term and see what I'm left with. I'm just going to do that in the next line here because it's going to be a little long. The limit as x goes to negative infinity of, if I FOIL this numerator, first terms are going to, that square root's going to cancel out. I'm going to be left with x squared plus 2. Outside terms, this square root times this negative x is going to give me negative x times the square root of x squared plus 2. My inside terms, positive x and this square root term, that's going to give me plus x times the square root of x squared plus 2. And then the L in FOIL, my last terms, negative x times x, that's going to give me negative x squared. And that's all going to be divided by, in this case, my denominator is nice and easy. 1 times that conjugate is going to be just the conjugate piece, square root of x squared plus 2 minus x. Now again, when we're using this technique of multiplying by the conjugate, the numerator gets really complicated looking, but then things are going to start to cancel out. This negative term is going to cancel with this positive term, and we're going to be left with the limit as x goes to negative infinity of what's left. We have x squared plus 2 minus x squared on that numerator, and our denominator is the same, square root of x squared plus 2 minus x. And it looks like this is going to continue to simplify because on my numerator, this x squared is going to cancel with this negative x squared. And I'm going to be left with 2 over the square root of x squared plus 2 minus x. So at this stage, we've got a pretty simple, easy to work with expression. So let's try substitution again and see what we're dealing with. So if I think about substitution, this piece here, this is what we said it was above. We said this was going to end up being positive infinity because we've got that negative infinity squared plus 2 under the square root. That's not going to change what's going on. It's still going to infinity. So this term here is going to go to infinity. This little x on its own is going to go to negative infinity, right? Because we're letting x go to negative infinity. This is where we have to be really careful with all of the pieces of our denominator here. This is the limit as x goes to negative infinity. Actually, I'm not going to write that limit expression because I'm kind of plugging in my values here. So this is 2 over, I've got that piece going to infinity in the start. Don't forget this negative, this minus, that goes right there. Minus this x on its own is going to negative infinity. So I'm going to put that in brackets here. Well, what does that give us? That gives us 2 over, well, those negatives are going to cancel each other out, infinity plus infinity, or two things increasing without bound being added to each other. And from the previous page, we saw that that is something we know in terms of a value or in terms of a behavior. Up here, something going to positive infinity plus something going to positive infinity is another thing going to positive infinity. So I can rewrite that denominator as something just going to positive infinity. And now if I think about this fraction, I have a constant divided by something that's getting bigger and bigger and bigger and bigger and bigger, which means that denominator's going to overwhelm the numerator, and this limit is going to just end up being 0. So a lot of work for not a very exciting result in terms of a number, but we've got the behavior of this function as x goes to negative infinity, which is exactly what we wanted with this limit. So I've got a couple other things to mention here that are really useful when you run into them when you're doing these types of limits. But before that, as always, I'm going to just show some pictures of these two functions just to emphasize what limits at infinity mean, what they represent, and to verify that these two answers look like they're correct based on a graph. So let's look at this one first. X to the fourth minus x squared. Let me bring Desmos over here, our good friend Desmos. I've got this one plotted here. So I've got x to the fourth minus x squared plotted. It looks like this. Now what we're doing in our example here is we're looking to see what happens to this function as we let x go to infinity. So in other words, if we look at our graph here, we're basically saying as x gets bigger and bigger and bigger, what happens to the function? As we go this way on the x-axis, what happens on the y-axis? And we can see pretty quickly as we let x get bigger and bigger and bigger, our function shoots way, 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 way up. It's increasing without bound. Positive infinity is our limit. So that's a visual example of something going to positive infinity or increasing without bound in the positive direction. What about this one? So the limit of this function as x goes to negative infinity, we said it should be 0. So let's see. So that's this function here in purple. So we are looking at this function and seeing what happens as we let x get big in the negative direction. So as x gets bigger and bigger and bigger as we go to the left, so negative 10, negative 20, negative 500, etc., notice that our function looks like it's approaching 0. It's getting smaller and smaller and smaller and smaller and smaller, closer and closer and closer to 0, the further to the left that we go, taking x to negative infinity. So if we were able to keep going here, we would see that this function would decrease without bound, getting closer and closer and closer to 0, which is exactly what we said for our limit. So this is something you can do on your own, and I definitely recommend doing this, especially when you're like just doing assignment problems or practice problems or studying for the midterms. With limits, I always recommend graphing your functions and just verifying it visually. You won't, of course, be able to do that on a midterm, but it kind of helps verify your answer in a visual way so that you're kind of seeing, okay, what's actually visually going on with this function behind the scenes, behind all the numbers, behind all the calculations. It just, I think it helps solidify what you're doing with the actual calculations. All right, now there's basically two things I want to mention here involving the thing that you might run into sometimes with these expressions when you're dealing with limits at infinity, and that is when you've got a square root of x squared. And this is where it's helpful to bring in the absolute value function. Now on D2L, there is or there will be a whole extra set of notes on the absolute value function if it's been a while since you've seen it or you haven't really worked with it. Sometimes you see it, but then you just kind of never see it again. So if you want a little bit more of a review on it than we're going to do here, I definitely am going to recommend you looking at that. It's going to be in the pre-calculus review section of D2L. But just as a brief review here, I do want to talk very briefly about the absolute value function. So the absolute value is a function, sometimes you'll see it called the modulus. When we talk about the absolute value of a real number, we denote it with that number in these vertical bars or brackets, and it's basically the non-negative value of whatever we put in those brackets. So the absolute value of 3 is 3, absolute value of negative 12 is 12, absolute value of 0 is 0. Nothing super exciting. But this can be a really helpful function when it comes to dealing with limits at infinity. Because, as we'll see, it can be really useful when we're dealing with this square root of x squared, which is kind of a weird term. And sometimes you might run into functions like this, for example, where you do have the absolute value in the function. So it's worth noting what to do with that when you're taking the limit. Now, one thing that you may or may not know about the absolute value function, depending on what you've done with it in the past, is that it is technically a piecewise function. Which means that depending on our input, the output of the function is going to change. So specifically, we can break this into a piecewise function based on if x, our input, is at least 0, or if our input x is less than 0, basically if it's positive or if it's negative. Now, sometimes this function, the way that we write this, can be a little bit confusing because it looks like we're making something negative when we just said the absolute value function basically turns everything positive. But this is where it sometimes helps to just draw a quick little picture as usual. I'm going to draw it. Let's draw it here. So I'm just going to draw a tiny little visual here for us. So let's say that our graph looks like this, and we're dealing with this absolute value function. Let's say we want to plot the absolute value function. So let's see what that looks like. So let's start with x equals 0. Let me actually color code this. X equals 0. Well, since I'm treating this as a piecewise function, I need to be careful and make sure I'm using the correct piece of the piecewise function. X being equal to 0 is in this part, x being at least 0. So the output of my absolute value function is just going to be the input, which means the absolute value of x is going to be the absolute value of 0 or just plain old 0. So I'm going to put that as a point here. Input is 0, output is 0, my point is 0, 0. What about x equals 1? Well, that's going to be the absolute value of 1. 1 is also in this piece of the piecewise function. X is positive, greater than or equal to 0. So my output of this is going to be just plain old 1. So my input is 1, my output is 1. That's going to put me there. What about negative 1? So now I'm taking the absolute value of negative 1. And in my piecewise function, now I'm down here. X is less than 0, it's negative. So what does that mean for my output? Well, my output is going to be the negated input. In other words, negative minus 1, which gives me positive 1. So here's my input, negative 1, output is positive 1. There's my plot. So it's kind of confusing because we have this negative here, but this negative is basically to negate all of the negatives for those pieces of input. And we could do the same thing for, say, 2. X equals 2 is going to be the absolute value of 2. We're back up here, so my output is going to just be plain old 2. And if I did say x equals negative 2, I'm taking the absolute value of negative 2. That's going to put me down here, which means my output is going to be negative 2 or just 2, which is going to put me here. So that's how the absolute value expression is expressed as a piecewise function. It looks a little bit confusing, but basically it gives you all positive numbers because this negates all the negatives in those negative inputs. Now, why am I bringing up the absolute value function kind of randomly in the middle of this set of notes? I'm bringing it up because if we're calculating a limit of something that involves this function somehow, remembering that this can be thought of as a piecewise function can really help us out. We can basically get rid of the absolute value bars and write that piece in terms of this piecewise function. So let's do an example just to demonstrate that here. Let's evaluate the limit as x goes to negative infinity of this function, the absolute value of x minus 4 over x plus 4. Now, if I think about substitution here, I'm going to have something that's infinite over something else that's infinite. I'm not too worried about the signs of these infinities. I don't, I know I just recorded this a second ago. I don't know if I mentioned this, but in terms of these indeterminate forms, this can be like plus infinity over minus infinity or minus infinity over plus infinity. It's still an indeterminate form. We don't really care about the signs because we can't do anything with it. As long as we have something infinite over something infinite, it's an indeterminate form. So this is another case where we can't just do direct substitution, so we need to do something with this. So let's see if we can rewrite this. Now again, this might look tricky because we now have this absolute value expression in here. And especially if it's been a while since you've worked with absolute values, you might be like, oh crap, what do I do with that? How do I deal with an infinite, or how do I deal with an absolute value expression when you're calculating a limit? And the trick is to remember this piecewise expression. So I'm actually let me make a note here before I write anything else. The way I'm going to do this is I'm going to look at two things. I'm going to look at my limit value, and then I'm going to look at my piecewise function. So I'm going to note that my limit is being taken as x goes to negative infinity. Now, if I think about that, x going to negative infinity, when I'm plotting this, or if we were to graph this function, my inputs here and here, technically, are going to be negative, right? Negative values of x. Which means for this absolute value piece here, I'm going to have negative something minus something. This thing is going to be negative. My input's going to be negative. And so what that means is I'm actually going to rewrite this as the corresponding output of this expression. So I'm actually going to draw some lines here. So this piece here is telling me that my input is going to be negative because I'm going to negative infinity. So that means I'm going to rewrite this x, the absolute value of x minus 4, as this. In other words, negative, then I'm putting that thing in brackets, x minus 4. So I'm basically using the piecewise function to get rid of the absolute value expression and write it as now just a negated parenthetical term. So I'm going to replace this with this. So I have the limit as x goes to negative infinity of, again, replacing this absolute value of x minus 4 with negative x minus 4 divided by x plus 4. I'm going to distribute that negative in there. That's going to give me negative x plus 4 on my numerator divided by x plus 4. And you can leave it like this. I don't like to have a negative term in the front if I can avoid it, so I'm just going to rewrite this as 4 minus x, just to make that numerator look a little nicer, over x plus 4. Now it looks like maybe a little bit more of an easier function to manage because it looks, we don't have an absolute value expression in there anymore. So let's see if we can use another one of the techniques we've talked about to simplify this a bit more so that we can use substitution. Well, I can't factor anything out here. I don't really have a common denominator thing I can do here, but I can do that technique that we talked about where see if I can find an example with it. I'm going to pause this so you don't have to see me scroll through everything, and then I'll show you an example. Okay, there we go. I was looking in the wrong set of notes. It's in the notes that we're currently in, the 3.1 notes on page 4. We talked about when we have a rational expression, one thing we can do is divide the numerator and the denominator by the highest degree term in the denominator. So we can actually do that here. We did that in the example on page 4. We did that in the example on page 5. Another example on page 5. Let's do another one here. So we're all the way back down here on page 8. And I'm going to note that my highest degree term in the denominator is just this x. So the highest degree term in the denominator is x. So I'm going to take my numerator and multiply it by 1 over x. I'm going to take my denominator and multiply it by 1 over x. So the limit as x goes to negative infinity. And now I have 4 divided by x minus x divided by x over x divided by x plus 4 divided by x. X is going to negative infinity. I have 4 over that. Even though it's going to negative infinity, that denominator is still going to overwhelm the numerator, and this thing is going to go to 0. Same thing here, 4 over x, same expression, that's going to go to 0. And these x terms, x over x, those are just going to end up being 1. So I'm going to have negative 1 over 1, which gives me a limit here of negative 1. And if you want to graph that function, go ahead and do it in something like Desmos and see if you can verify visually that that should be the limit as x goes to negative infinity. Now this absolute value function can also be helpful when, like I mentioned, we end up with something like this in our expression. Because, I'm going to go to the last page here. for any value of x, we can actually express the square root of x squared as the absolute value of x, right? Because this is essentially doing what the absolute value function does. When I have something squared, let's say x is, I don't know, -10. If I have the square root of x squared, that's going to be the square root of -10 squared. The squaring is going to act as the thing that gets rid of the negative, so that's going to be square root of 100. And the square root is going to just bring us back to the positive value of our input. So these are equivalent in terms of what they give you back. For any value of x, the square root of x squared is going to be the same as the absolute value of x. The thing is, though, is that the input can be either positive or negative. So the x that we're plugging into these functions itself can be positive or negative because, like we just saw up here, square root, or the square of a negative is going to give us the same result as the square of the positive of that same quantity. Now this is something that in past times I've taught this course, this can be kind of convoluted, and some people are like, why do we do this, or what is the purpose of this? It's basically to deal with situations where we need to care about the sign of x. Specifically, in situations where we're dealing with limits at infinity, where x could be going to either positive infinity or negative infinity. It's essentially a way for us to make sure that if we were looking at a graph of this expression, we would be looking in the correct direction, because sometimes the limit value will change depending on if we're taking the limit as x goes to positive infinity versus x going to negative infinity. It's kind of a pain because we have to rewrite some stuff and take some stuff out, but this is a useful way to work with that square root of x squared term and make sure you're getting the correct result. So let's look at this in the context of an example, and I'll kind of talk about this as we go. So here, we want to evaluate the limit as x goes to positive infinity of this expression, the square root of x squared plus x, all plus 3, divided by 2x. So I'm going to go ahead and start by just rewriting this. So square root of x squared plus x, all plus 3 over 2x. Now I'm going to do something here that's a little bit weird, but it's going to help us out here in a second. I'm going to factor out an x squared in this square root term, which is going to look kind of strange, but like I said, it's going to help us out here in a second. So I'm going to still write my square root here, but now I'm going to factor out an x squared. So if I factor out an x squared in those terms under this square root, I'm going to be left with 1 plus 1 over x. And then I've got that plus 3. So basically I'm rewriting this so that if I were to distribute this x squared back in here, I would get the original expression. And if it's been a while, or if you're not comfortable doing that, sometimes it helps to like work backwards and check your work. If I were to do that, x squared times 1 plus 1 over x, if I distribute that x squared back in there, do I get this? Let's see. So x squared times 1 is x squared, plus x squared times 1 over x is x squared over x, which is x squared plus x, which is what this thing is. So I'm basically pulling out an x squared, which right now seems a little arbitrary, but we'll see how that works for us here in a second. And then my denominator here is just going to stay 2x. Now what I'm going to do is I'm going to take the square root of x squared and write it as its own term. So I'm just going to write this first and then do it. Separate out this square root of x squared term. Just think of this as some special weird thing that we need to consider when we've got square root terms with these types of limits, because like I said, this is going to be the thing that can maybe determine if you're doing the right limit in terms of the sign or the incorrect one. So it's important to think of and rewrite. So I'm going to put this in brackets. And I'm going to make a note here. If I have the square root of something like a times b, the nice thing about this product under a square root is I can break it up. I can rewrite this as the square root of a times the square root of b. Those are equivalent in terms of their value for a given a and b. So let's see what that looks like. So I'm basically going to take that square root of x squared out of my numerator, and I'm going to multiply it by the square root of whatever's left in there. That 1 plus 1 over x, all plus 3, all divided by 2x. And then the other thing I'm going to do here is I'm going to rewrite this square root of x squared as the absolute value of x because of this relationship up here, which again seems maybe a little bit convoluted, but we're trying to simplify things. We're trying to make sure we get the right sign of our limit. So let me rewrite this one more time. The limit as x goes to infinity of, I'm going to rewrite that square root of x squared as the absolute value of x. That's times 1 plus 1 over x, all under the square root, plus 3 divided by 2x. Now, that doesn't look any easier to deal with, but as we'll see, we're now at the stage where we can actually use the same trick we used up here. We can look at the highest degree term in our denominator and divide both the numerator and the denominator by that, which is kind of nice here because our denominator is really simple. We don't have any square root terms or anything like that. Our denominator is just 2x. So I'm going to multiply both my numerator, or sorry, divide both my numerator and denominator by x. So I'll make a note here. Highest degree term. We're kind of putting everything together in this example. So highest degree term in denominator is just plain old x. So I'm going to multiply my numerator by 1 over x, and I'm going to multiply my denominator by 1 over x. So the limit as x goes to infinity of, I have this absolute value of x times the square root of 1 plus 1 over x. I'm going to put that whole thing over x plus 3 over x. So there's my 3, I'm taking it, dividing it by x. And then same thing on my denominator, 2x divided by x. Now, I'm going to, again, take a look at this. This is my absolute value function. How did we deal with this in the previous example? Well, we looked at the limit value, and then we rewrote, got rid of the absolute value expression by looking at the piecewise function. So here, I'm going to note that x is going to infinity, positive infinity, with our limit, which means I can rewrite this absolute value as just plain old x, because based on our piecewise function, if our values of x are positive, then we just drop the absolute value bars and write our positive or non-negative value as our function. So I can actually completely drop the absolute value expression here and write this as x times the square root of 1 plus 1 over x plus 3 over x, all divided by 2x over x. Now we're starting to get some things that are going to cancel. This x is going to cancel with this. This x is going to cancel with this. We've got the limit as x goes to, well, let me write this down here. We have the limit as x goes to infinity of, now we just have 1 plus 1 over x under the square root plus 3 over x, all divided by 2. And now if I try substitution, I try plugging in that limit value of infinity. This 3 over something going to infinity is going to go to 0. This 1 over something going to infinity is going to go to 0. So we're going to have what's left? Square root of 1 plus 0 over 2, which is the square root of 1 over 2, which is just 1/2. And that 1/2 is our limit. So a little bit of extra work, a little convoluted. If this had been going to negative infinity, we would have replaced this x with a negative x. So if x had been going to negative infinity here, the absolute value function would be replaced with negative x, which would have changed the sign of our limit. And let me actually, let's visualize that. So let me close that. What is our function here? So this is going to be, just do this in real time here. This is going to be square root of x squared plus x, all plus 3, and all divided by 2x. So this is a funky looking expression, but it looks like this. Now, what did we say in our limit calculation here? We said as x goes to infinity, the limit of this thing should be 1/2. So visually, as we're shooting off in this direction, what we should start seeing is we should start seeing this function, the y coordinate, get closer and closer to 0.5. So closer and closer and closer. It's not going to drop below 0.5. It's going to approach 0.5. Now, if we think about the other direction, though, say the limit as x goes to negative infinity, what's that going to be? Well, visually, we can see that that's going to be this side of the graph, and it looks actually like it's going to be negative 1/2, which if we think about what we just did with the absolute value function and what I just mentioned there with this piece, if this had been going to negative infinity, this would be negative x, which would, at the end of all these calculations, the only thing that would change is it would make this negative 1/2, which is exactly what we're seeing as our limit if we were considering the limit as x goes to negative infinity. So this sort of thing you're not going to run into a lot of, but it is a worthwhile technique to know because sometimes the sign of your limit is going to depend on the sign of the infinity that you're heading towards, whether it's increasing without bound in the positive direction or increasing without bound in the negative direction. There is a slightly faster way of doing this. I'll show you that in class. Just to show you another way of doing this using that shortcut. But this is kind of the longhand and the really making sure you've got the signs right kind of a way of doing it. So I wanted to show this to you in the video just so you can see how that absolute value function can actually be helpful. Sometimes even if you don't have an absolute value expression in your function.